aim of the present talk is to see how we can use Macaulay tool in the actual principles. We begin with our animal. We are talking about redundant sampling. That is a three-dimensional simplicial sphere with h vector 191691, which is obtained from the boundary of a false replace after a certain number of stereo subdivisions. And now you will ask why we call it dodgy. This is the classical question. And I will reply that it's a very stable animal to which gives all the time counter results in our conjecture. And also it helps us in our group to know for what example we're talking about. Okay. The base idea of the down V, which are denoted by ID, is equal to this. It's a little bit complicated. And the first question that we want to investigate using Macaulay tool is does the phase link related to D satisfy which sets properties? Then we will set property first, and after that, the stroke system. We are working over Q, so the first thing that we should do is to define a phase. We have 13 variables, x1 to x13. So we denote by the polynomial D, as we mentioned in my previous Macaulay talk. We write down now number of variables, and we set it equal to 13. The next step is to write down the idea. We write down explicitly the generators of ID. And the first thing that we are asking is, which is the true dimension of them? By using D, we have seen these commands in my previous talk. So, Macaulay tool returns that the true dimension is equal to 4. So we have 3 dimensions. One less. We denote by writing the ideal which is generated by 4 random linear elements, and we use apply. We said that apply is a type of function that gives us 4 linears in mass instead of writing down each linear step by step. And the first thing that we should say is if these 4 linears form a regular sequence. Okay. So we add 4 linears in our initial ideal, and we compute the full dimension. And we check if the dimension is dropped by 4. If this happens, we have that this sequence is a regular sequence. The next step is to and this is this one gives us the linear reduction. So the next step is to compute the H vector of the linear reduction by using the command filter function, as we discussed before. And it says that yes, the H vector is equal to 1, 9, 16, 9, 1. The first question that we should answer is if this D has a weakness set property. So we consider a linear element by using random 1R, between 1, and we should compute the concurrent arithmetically of multiplication by this element. Okay. So we have this linear element to the idea of generic reduction. and we compute the Hilbert function. And it says that this equal to 187, which means it's the kind of group because it's a general element that is a with less than. So we have a with group. Next step, we should check if we have the stronger set problem. Here is a double check in the sense that first we should check the multiplication by L4. So in our ideal, we are the ideal L at 4. And according to the pairing, we care about the fourth entry of the Hilbert function vector. So it says that it's equal, right? Hilbert function 4, the fourth will be part, R over 1 up to J2, J2 is right here, and it says that it's equal to 0. Okay. For the second pairing, we use the command basis 1R in order to take a basis of one graded piece, we do the piece of degree 1, and we multiply each element of this basis by L squared, and we check again the multiplication. For the pairing between the first graded part and the third graded part. So we use again the command Hilbert function 3. Now we care about the third graded part. We are just focused on the pairing. Okay, about this statement. And it says that it's equal again to 0. So we are fine. We have a proof using computer that RD has the weaker set property and also the stronger set property. Okay. In the next slides, I want to discuss how we can use computer in order to compute a projection. But let's remind you what is linear projection. From yesterday's talk, the substance of linear projection is that we are starting by the dimension 1 ideal, which lives in a Goldstein ring, such that the quotient field is time. In this case, the codimension is increased by 1. We denote by I the canonical inclusion, and under this assumption, as we discussed yesterday, we prove that there exists an extra homomorphic for phi modules, which we are denoted by phi, such that code is generated by the inclusion map, and this phi as an null module. And we defined yesterday that the projection link is this course. The question is how we can use Macaulay 2 in order to have the final link. Okay, first we should use it in order to check the assumptions of this linear projection. And if the assumptions are satisfied, we can use Macaulay 2 in order to compute code, firstly, and then write down the final link, the projection. As Mark says, Macaulay 2 computes code and Vasiliki as a module. But there's also Macaulay 2 patterns, which doing the same thing and is much more than that, which is called Pushkin-Miller. It is created by Jack Bell and Stanford Combinatorial. We don't use the package here, but if you're interested, you can check the website, the quality website to see more details. And also the related paper in the journal of quality. Okay. We will use Macaulay 2 to compute the projection for the example that we discussed yesterday, for the example of probability intersection inside the probability intersection. So again, we are working over Q. We denote by S the polynomial in variables X, Z, Y, W. We denote by F this polynomial, yes, and by IX the ideal is generated by this polynomial, and by I the ideal X and Y. The first thing that we want to check is if the ideal IX is contained in ideal I. How we can do it? By using is sub. So is such that IX, comma Y, according to says that it's true. We can also check if the ideal IX is prime by using this prime, and it says that yes, that's true. And the next step is to compute whole. How we do it? We use the command whole, the ideal, and this is the Gaussian. Something is missing here, so for that. The next step is to check the Betti table of the resolution 10. It says that we have two generators, so we are fine. The first generator is obtained by using homomorphism f m underscore 0, and the answer is that is x comma y. So this is the utility map. And the other homomorphism, which is obtained by using m underscore 1, is the file that we are caring about. And it says that it is defined by this. Okay. Next, we use res in order to compute the resolution. Okay? By CDD1, we can use it in order to take the homomorphism. And now we have our phi, so we are ready to write it down, our final link. As we said before, we put the mirror projection to dimensions increasing by 1, and we add a new variable. The new variable is denoted by T here, and we should define a new ring, which is the polynomial ring that we had before, plus one new variable. The variable which corresponds to a projection variable, to our new projection variable. By using sub IX, new R, we help Macaulay to understand that we want to see our ideal IX in our unit. Okay, to the new R. And this multiplication, the ideal which is have these generators, is the way to, as we said yesterday, our unit will have something like Tx minus 5s and Ty minus 5y. So this is the way that we can use Macaulay in order to write down these generators. Okay, where phi y and phi x and phi y. By this computation, we know that phi y goes to this, and phi x, sorry, goes to this polynomial, and phi y goes to this. Okay. So using this command, this multiplication, we have my way to write down these two generators, okay? One idea. Are there any questions so far? The next step is to check if our items run. This is important when you want to use distributing arbitration in order to have applications in algebraic geometry. In the sense that if you want to construct some surfaces with a type of threefold, you should know that the rig that you construct is an integral domain. Okay. And the next step is to check if our idea is homogeneous. We are using the command is homogeneous at the name idea. And it said, yes, it is. The dimension idea by using the command for D. And it said that it's equal to 2. And also the better table. We should make this checking because we should be sure that in the end, we take the link that is Einstein. Because the general theory said that Miller arbitration is a theory that produces a Einstein as a final. Okay. So the dimension is 2, the length here is 2, so we are in a, we have a Combinatorial. And if we check the last column, we see that there is only one non-zero element, which is equal to 1. So we have a Einstein. And that's fine. It seems that we used the in a good way when we take memorization. Because, for example, if the final block that there's no Einstein, maybe we had a mistake before. Okay. And we should go back and find it. Okay. In the last part, we want to use Macaulay 2 in order to follow the steps of our main proof with Stavros for generic anisotropy of simplicial spheres over a field of characteristic 2. For simplicity, we will focus on one-dimensional spheres here. So our theorem says that assume that we have a field of characteristic 2, and this is a D minus 1 simplicial sphere. What we have proved is that D is generically anisotropic over K. As mentioned before by Karim, there is a restriction in characteristic for our theory, but there is no restriction about dimension. It goes for any dimensional simplicial sphere. So as I said before, for simplicity, we assume that D is a one-dimensional simplicial sphere. In practice, we have a proof for one-dimensional sphere for any field, but I want to give the argument for the general case. That's why I'm focusing here on the one-dimensional spheres, and then we follow our main steps for the general case, but for one-dimensional spheres. Okay. Assume that n is greater than or equal to 3, and D is the boundary of the n-gon with vertex set 1 up to n. The convention is that 1 is connected to the vertices n and 2. The vertex I is connected to the vertices I minus 1 and I plus 1, when I is between 2 and n minus 1. And the vertex n is connected to the vertices n minus 1 and 1. Which means that we have this picture. 1 is connected to 2 and 4. Okay. If n is greater than or equal to 4, we can write down the standardizing ideal which corresponds to D. It has this form. And if m is equal to 3, we have the standardizing ideal which is related to the freedom is x1, x2, x3, the boundary of the freedom. We set x sigma to be this product, and we denote by bracket ij the determinant of this matrix. For example, if we are working with the boundary of the freedom, assume that our V is the boundary of the freedom. We know that the ideal which is related T is x1, x2 is T. We know that the new dimension by D is equal to 2. So in order to obtain the generic reduction, we need two linears, F1 for that. We know by epsilon, the ones field. The epsilon is just that until the exact extension to these values. We consider two linears, L1, 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 L2, 2, L2, 3. Okay. And we do not by A, the generic linear reduction, which is string past two. Okay. This is my opinion. It is called generic linear reduction. Now, we denote by N the matrix which has as rows the coefficients of two linears, these two linears. So L11, L12, 3, L1, L2, L3. Okay. What we denote by bracket 1, 2. Where the first form and the second, we form the matrix, we define the matrix. And we're taking the determinant. Okay. In a similar way, for example, with bracket 1, 3, we use the first and the third column, and we get again the determinant. This is what we denote by bracket out J aspect. Okay. Assume now that sigma tau, well, are two facets of D. Then, to achieve this relation, that bracket sigma is equal to bracket T XC with the quality in A. Okay. The proof. We work on the rate, and by using gas elimination, we have that sum from I1 up to n bracket 2i xi is equal to 0. In practice, here, we multiply this by 8-1, and we multiply this by 1-1. Okay, this is our 1, not F2. A1 F1 plus A1 1 F2 is equal to 0 because it belongs here, right? To the quotient. So we have a A1 A1 2 minus. I'm going to characteristic too, so signs are not important. Okay. So plus A1 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 A3 3 is equal to 3. So this corresponds to bracket 1 2, and this corresponds to bracket 2 3. These are the determinants. Is it clear? Yes. Which? Okay, the last line is obtained if we multiply this. Okay.
I guess, sorry, I'm just where we are from the bottom to the like.
I will try to explain how we can make this last relation. Okay. Yeah. So here if we multiply by x1, we have that 1 2 x minus 2 plus 2 3 x minus 3 is equal to 0. Okay. The difference with the slides is that here I eliminated x1, but in slide we eliminate x2. Okay, I try to explain how we can pass to this relation. Okay. The code which is related with that is that we will try to take this relation for every sigma tau, for every pair of faces of our initial thing. So we use this for loop in order to have variables A11 up to 85. We denote it by this way. We are working over a field of characteristic 2. We define our polynomial ring, and we have our metrics. The metrics is the metrics that I explained here. This function returns the determinant of the 2 times 2 submetrics of the metric cell. By this, we can determine the rows and the columns. Now we use apply in order to have as a sequence the variable x1 up to x5, and then we transpose the metrics. We denote by ID the idea is standardizing the thing, and by I the idea is the negative like that. We choose B1, B2, B1, B2. We want to check about to check the relation for facet for the facets 1, 2, and 2, 3. Initially. So we denote by B1 the bracket 1, 2. We compute the bracket 1, 2 this way, and with U2 the bracket 2, 3. And the first thing is that bracket 1 x1 x2 plus bracket 2, 3 x2 x3 is 0 for the specific. And then we will use a for loop. Here we have the face list. If we use the face list for a member, starting by N1. And with this for loop, we check our relation for each pair of facets. Okay. And so that for every pair of facets of the cycle, we are done. Our relation for. You will this relation that bracket sigma is equal to bracket xt. We have that we denote by volume from A to epsilon, be the unique linear isomorphism, which is defined like this, 1 over bracket sigma. We have different names for this. We have volume, we have psi in the original Petrotou. We have degree. Many different names for the same thing. And using again Gaussian relation without denominators, we can compute volume U for its monomial U in A. And this proposition gives some formulas for the monomial. So this proposition is related to computations of the on the linear reduction in different monomials. And how we can implement this with Macaulay 2? We are working with the user cycle. We define our unit metrics and determine the brackets as before. Our ideas. We choose a basis element, this element x1, x2. And more or less what we are doing here is to multiply and denote them as ideas. So we choose here. We use again the command subset. we check our relations, and my colleague said that yes, that's true. We have these formulas. And the last proposition is related to some differential identities that we have already mentioned in previous talks. Actually, sigma toward faces of D of dimension 0, we will have these differential identities which are mentioned in Karin's talk yesterday. We'll create a sigma to no differentiation with respect to this variable. We will take these identities again with the Macaulay 2. We are working again with the triangle, we denote by M the matrix of the coefficients of the files. With this function, we compute the determinant of some matrices. By D13, we denote the bracket on 3, by D1, and so on. We have brackets. We can differentiate an monomial. We can differentiate in Macaulay 2 using the command D. So we define a D fraction for differentiation to some variables, and this times double differentiation. This an operator of second order. Please D11. Okay, we care about volume x squared. Would run by our formulas is equal bracket 1, 3 over. Okay, we want to have a differentiation in this rational. Okay, first we care about this square wall x square. And how we can do it by using these times, which means differentiation 3 times. And we care about the variables of the differentiation. And fraction is, we write down this expression. Okay. More or less with the following commands, we check our differential identities for every pair of variables in a column in our list. And Macaulay 2 said that yes, it's fine, it's false. And the next proposition said that these differential equations, it falls also for a polynomial, not in A1, not just monomials. And the proof is a combination of peculiarities of characteristic 2. Nothing difficult. We write U as a linear dimension of A1, and we take square. Square goes out of the operator, and we finally have the last relation. You can find more Macaulay proposed related to operator in this archive version, in the archive version 1. Some references. These are the books that we discussed before. And an announcement. In September 2024, 2026, we organized with Karin and Stavros a workshop in combinatorial geometry who will take place in Manila. And we will be more than happy if you join us. You can use this web page. For existing, there is available funding, so. And that's it. Thank you very much.